Hello and welcome to our instructional video on the functions and their graphs. We will focus on the topic of operations and functions for this one. So these are the notations that we will use for our operations and functions. The first one is for the addition of functions. This is for subtraction of functions, multiplication or the dot product, and is for the division. It's actually a lot easier than it looks. It's actually very straightforward. What operation you see in there is what you will do. And here I'm showing you the arithmetic operations so that you have an analogy between arithmetic operations and operations on functions. So for any real numbers a and b, so you could imagine that a and b are two different numbers. It's easy to calculate these four: a plus b, a minus b, a times b, a divided by b. And of course here b cannot be 0, otherwise this will be undefined. So going back to the operations and functions, it's actually really very simple. It's nearly as simple as the arithmetic operations. You just have different terms that you are adding, subtracting, multiplying, or dividing. And it's just that the notations look more complex. It's actually very straightforward. Here you have the f plus g of x, the notation for the addition. So it's just adding the two functions f of x and g of x. So this one is just adding the two functions. As for subtracting, if you get f minus g of x, is just equal to f of x minus g of x. And for the dot product or multiplication, f times g of x is just equal to f of x times g of x. And for f divided by g of x, f over g of x, is just equal to taking your two functions, f of x divided by g of x, f of x over g of x. And as similar to the arithmetic operations, the divisor, in this case g of x, it cannot be 0. So this is going to be important in getting your domain later. So these are the notations for your operations and functions, and this is how you calculate them. So to illustrate to illustrate further, we'll have some examples. For our first illustration, this is our example. So you suppose that you have f of x equals 2x plus 3 and gx equals x minus 5. What is going to be the value of our operations? So this is what we will explore. Here, the operation addition, f plus g of x. As defined, it's just the addition of the function f and g. But what are your f and g? It's given in the example. So you just use these expressions here. Use these expressions and substitute into the equation. You get 2x plus 3 plus x minus 5. Combining like terms, you have 2x plus x, 3x, 3 minus 5, negative 2. And that's already your final answer, 3x minus 2. How about the domain? Well, you could just observe what kind of values your x can take. And it's pretty much any real number you could think of. So that's why we have here domain f plus g is equal to x such that x is a real number. So it's an actual sentence that describes what kind of x, any real number. So don't forget the curly braces because this is a set. Or alternatively, you could use some more mathematical way of writing. You could put in domain of f plus g is equal to x such that x is an element of the set of real numbers. So this expression here says that x is a real number. And either of these two, you can write down as a final answer for your domain. Evaluating the subtraction operation, so f minus g of x, we have defined it as f of x minus g of x. We substitute this expression to f of x and this expression to g of x. And you get this one, 2x plus 3 minus x minus 5. I've just distributed this negative sign to this expression, and that's negative x plus 5, and I just remove those parentheses there. So we combine like terms for this step. We get 2x minus x, x. 3 plus 5, 8. And that would be your final answer for the final expression. What is the domain then? The domain of f plus g is x such that x is a real number. Again, we're just saying that x can take on any real number, and this equation would still be valid. Alternatively, we can write this expression, this long one, into a shorter one, to set x such that x is an element of the set of real numbers. This expression just says that x is a real number. So multiplication of functions, f times g of x. So we're going to have here as defined f of x times g of x. So f times g of x is going to be 2x plus 3 times x minus 5. How did we get this? We just substituted the expressions for f of g and f and g into this equation over here. So let's just be meticulous in distributing the terms of the first expression to the second one. 2x times negative 5, and distribute 3 times x, 3 times negative 5. We're going to get this. So you could practice that on your papers. And we combine like terms, we get 2x squared minus 7x, these are like terms, minus 7x minus 15. So that is your final answer. As for the domain, it's just x such that x is a real number. So we're just saying x can take on any real number. And we could write that in the shorthand x such that x is an element of real numbers. So any of these two will suffice as an answer for the domain. All right, and as for division, f over g of x is just defined as f of x over g of x. It's just dividing the two functions. So we substitute the expression for f and g into this. We get 2x plus 3 over x minus 5. And that's already your final answer. But as for domain, this is going to be your clue as to what the values of x are. So we put that to the side, g of x not equal to 0. And we just substitute this expression, x minus 5 not equal to 0. We transpose this to the other side. We get x not equal to 5. So we're going to include this in our expression for the domain, which is this one. The domain of f over g is equal to x, which is a real number. X is a real number such that x is not equal to 5. So what we're saying here is x can be any real number except 5. That is your domain. So why can't it be 5? Because if it's 5, your divisor becomes 0 and this will be undefined. So that's why we're avoiding 5. But how about g over f? Is this the same as f over g? So that's what we'll see. Let's check. So g over f of x is equal to g of x over f of x. We substitute the expressions and we get this. And it's obviously different from this one. But how about the domain? Well, let's see about the domain. So we'll put this down here. F of x not equal to 0. So what's f of x? It's just this one. 2x plus 3 not equal to 0. We transpose this to the other side. 2x not equal to negative 3. And we divide this by 2 so that we can isolate x on the left side. You get x not equal to negative 3 over 2. So this is going to be, the negative 3 over 2 will not be included in the domain. So we write it as this. The domain of g over f is x, which is a real number, such that x is not equal to negative 3 over 2. That would be your domain. As you can see, it's really different. These two expressions, operations are very different from each other. First is the expression itself is different, and then the domain is different. So that's how you calculate this. All right, so here's another example. So suppose big F of x is equal to x squared minus 3x minus 6, and big G of x is equal to x cubed minus 5. What are the values for these? What are the expressions? Furthermore, let's evaluate, as after getting the expressions here, let's evaluate the values if x is equal to negative 1. So we'll see what happens. For f plus g of x, this is just f of x plus g of x. We get this. And I think the only like terms here are the constants, which is negative 6 and negative 5. So we get this. Oh, I also rearranged from left to right, from the highest exponent to the lowest. So we have x cubed, x squared, minus 3x, and minus 11, because negative 6 plus negative 5, negative 11. All right, so that's your final answer. As for the domain, it's just any real number. So I used here the shorthand because it's easier. So that's going to be your domain. At x is equal to negative 1, we just take this expression here, this one, put it way over here, f plus g, and then I substitute x with negative 1. So as you can see, all the x's have been changed into have been changed into negative 1. So this is going to be negative 1 because negative 1 times negative 1 times negative 1, see cube, the third power here. So you get negative 1. And this is since it's an even exponent, it's positive 1. And this is plus 3 minus 11. It is plus 3 because negative 3 times negative 1. Evaluating this, we get negative 8. So this is your final answer for f plus g of negative 1. It is equal to negative 8. As for this, f minus g of x is equal to f of x minus g of x. The expression f minus the expression g, so we distribute this. So you're going to get negative x cubed plus 5, and this one I just copied right down here. You combine like terms and you get, I also, again, I rearranged, of course. So negative x cubed is way over here, x squared is on the second spot, negative 3x is on the third spot. So negative 6 plus 5, negative 1. And we have this as our final answer, and the domain is just a real number. So that's your domain. So how about at x is equal to negative 1? So we get f minus g of negative 1 is equal to negative quantity negative 1 to the cube. So every x I just exchange with negative 1. But this is separate. This separate from the x. That's why it's still outside. Evaluating each of those, you get positive 1 because this is going to be negative 1, right? Times negative, so positive. And this is going to be positive 1, and this is going to be positive 3, negative 1, and you get 4. That's your final answer for f minus g of negative 1 is going to be equal to 4. How about for multiplication? So it's going to be just similar steps with our previous example, but you're going to have to be a little more, a little extra careful with distributing the terms. So you get here x to the fifth is just that one, and minus 5x squared minus 3x to the fourth, positive 15x minus 6x cubed, and positive 30 over here. So just be careful with multiplying, especially with the signs. Rearranging that, we have this, and there are no similar terms, so this is already your final answer. As for the domain, it's just the same with the previous ones. X such that x is an element of real numbers. How about evaluating this expression at x equals negative 1? We have this. Okay, so We just put this way over here, but exchanging all the x's with -1, and this is going to turn to -1 because it's an odd exponent, right? So it's a -1. Even exponent, so it's positive. So -3 maintains the sign. This is going to be -1 times -6. That's why it's positive. So -5, -15, and +30. So we add and subtract. We get f times g of -1 is equal to 12. That's your final answer. How about this one? So division, f over g of x is equal to f of x divided by g of x. So we substitute the expressions of f of g, we get this. And this is already your final answer. There's nothing more we can do about that. And let's explore what values x could take, because we know that g of x is not equal to 0. But how about x? So we write this on the side here, just like a scratch paper. G of x is x cubed minus 5, not equal to 0. We transpose to the other side. We have x cubed not equal to 5. We take the cube root so that we'll eliminate this exponent here. So we get x not equal to cube root of 5. We put that in our domain. So the domain of f over g is x, an element of real numbers, such that x is not equal to cube root of 5. Right? That's your final answer. Okay, now composition of functions. It is another operation on functions. So it's actually very different from the other ones. Let f and g be functions where the range of g is in the domain of f. You should remember our illustration on the domains and ranges like baskets. So this time we'll have another illustration, but it's a little more complex than the last time. So we have two machines. Two machines. It's f and g placed side by side. So the domain of G, as you know, it's like the basket containing all the x's that we could put into G. As for the range of G, it's the basket of values of y that we could assign to x. So whatever comes out of this machine, it comes out and goes into f. The range of f is going to be the values that we could assign to whatever comes in. So we have here the domain from the domain of G. You put in x, and then the machine assigns a y. So you get this, and it becomes g of x, right? And this g of x, this value, it continues and goes into the function f, and then the machine f assigns a value z to g of x, assigns that, and it becomes f of g of x. And that's the final output of this machine. So the composition of f and g is just given by this expression here. So you might be able to see this more often. This f circle g of x is just equal to f of g of x. So what is going to happen is that the expression for g you put into f. That's all that happens with composition of functions. So to illustrate that further, we'll have some examples. So suppose f of x is equal to fx minus 7 and g of x is equal to 4x squared minus 3x minus 6. How about what's going to happen to these composition of functions? So we'll see. First, f circle g of x, and as defined, is just this: f of g of x. If you could see more closely, uh, this one is pretty much the same as this. It's just that your x over here we exchanged for g of x. See, the x became g of x. So this is going to be what's going to happen. So your f of x, yeah, we know this to be this. So all the x's we exchanged with the g of x expression. So this is 5x, right? 5, the x becomes this. That's all that happened. So 5 times this quantity minus 7. So we distribute, we get this expression. And we combine like terms, negative 37. That's your final answer. How about evaluating at x is equal to negative 1? So we substitute all the x's of this expression with negative 1. We get this. Because this is going to be positive 1, 20 times 1, 20, negative 15 times negative 1, positive 15 minus 37. That's just negative 2. That is your final answer for evaluating at x equals negative 1. How about g circle f of x? So this time it's going to be g of x. That's like the quote unquote mother function. And then we put in f of x into this. This I'm doing this a little more slowly. So if this expression is just this one, it's just this one with all x's exchanged by f. Look at this, 4x squared, right? 4x squared, and you have 4, 5x minus 7 quantity squared minus 3x. So it's minus 3. The x is exchanged by 5x minus 7 and minus 6. And we expand this. We expand these expressions. We have this. So you have to be careful with expanding and multiplying, especially with the signs. So we expanded this, it becomes this. And this negative 3 we distribute, and that's why we have this. I also distributed this into the next expression, and then also simultaneously I combined like terms. It's this one, 4 times 25x squared, this one, 4 times negative 70, 4 times 49, minus 15x plus 15. Right, and this is going to be your final answer for this expression. No, wait. I'm sorry. There are still some like terms, these x's over here and these constants, and that would be your real final answer. Oh, and as for evaluating at x equals negative 1, just exchange all the x's with negative 1, and we have this. See? So negative 1, we evaluate this at an even exponent, so it's positive 1, so just 100. Negative 295 times negative 1 minus 211. We subtract and add, and we get this. So those are your final answers. Okay, so putting it side by side, those two operations we just did, f circle g of x and g circle f of x, we have here a very different expression. So this one is 20x squared minus 15 minus 15x minus 37. And this one is really different from this one. Evaluating at x equals negative 1, we also got different values. However, you can also observe that the domains are the same. The x's can take on any real numbers for both expressions. So sometimes in some items, you'll be given just one single question. What is the domain of G circle of H? So how do you do this? First, you evaluate the expression of G circle H. Then you investigate what the domain would look like. All right, let's have another example. So suppose g of x is equal to a 6x minus 5 and h of x is equal to 1 over x. So g circle h is equal to 6 and quantity 1 over x. So the x I just exchanged with h of x, which is this expression. So we have this. And 6 times this quantity minus 5. See, it's just the same. Distributing this here, we have 6 over x minus 5. So the domain of G circle H is x any real number such that x is not equal to 0. So where did we get this? We got this by observing. By observing this expression, we can see that we can't have an x being equal to 0 because this would be undefined. That's why this is our domain. This is our final answer for the question, what is the domain? And that is it for the operations on functions. It's very straightforward. What you see is what you're going to do. If it's addition, you just add. If it's subtraction, you just subtract, and so on. Except for the composition of functions, which is like just exchanging all the x's with another function. So it's actually very easy, and I think I'll see you in the next